We are diving straight into Mull-Tokens, Modality-Agnostic Latent Thinking. This is a paper that really gets at one of the biggest efficiency problems in modern multimodal AI reasoning.
It does. I mean, if you're an ML engineer who's dealt with visual puzzles or IQ tests or any kind of complex spatial task, you know this pain point.
Absolutely. The models, even with chain of thought, they're just brittle. The text rationales, they start to drift, right? They just detach from the visual input and you start getting errors.
And for so long, the solutions were either, really clunky, like relying on external tools, or they were just tremendously expensive, demanding that you generate entire intermediate images at every single thinking step.
Mull-Tokens offer this third path, and it's just remarkably simple.
It is discrete, fixed-length, latent tokens that act as an internal kind of multimodal scratchpad.
So the model gets its own private space to think freeform. It can handle computations like spatial mappings or depth predictions using this abstract modality-agnostic language.
And the performance hook is really powerful.
Oh, yeah.
Mull-Tokens delivered an average gain of over 3% in accuracy across some really tough reasoning tasks.
But the real attention grabber, for me at least, was the efficiency gain.
Right. Especially in the hardest splits. On complex visual puzzle solving, they saw an improvement of up to 16%.
16%?
All while using just 10 to 40 of these latent tokens. So inference becomes dramatically faster, cheaper, way better than generating these verbose text rationales that can run to hundreds of words.
So you get performance and computational efficiency. It's not a trade-off.
Exactly.
Okay, let's unpack that central challenge. Why did textual chain of thought, which was so transformative for verbal logic, why did it fail so spectacularly when you add visuals?
It really comes down to the kind of manipulation that's required. Text is great for sequential logic.
Yeah.
A leads to B leads to C.
Sure.
But when you ask the model to imagine a 3D object rotating, or to mentally shift pieces of a jigsaw puzzle around, that internal process isn't really linguistic.
Right, it's spatial.
Exactly. And trying to force that into a sequence of words like, first I rotate the cube left, then I check the color. It's just inefficient and often completely insufficient.
And that inefficiency is the drifting they talk about.
Precisely. The model starts its little textual monologue, but pretty soon the reasoning steps don't actually track the visual data anymore.
It's like you're describing a process you haven't actually internalized visually.
Right. And previous attempts to fix this they hit dead ends. The tool-augmented designs, for instance, are brittle.
Oh, so?
Well, if the reasoning needs an internal action, say mentally cropping an image or zooming in, you have to design a whole explicit external module for that. It's indirect, and it's really hard to generalize.
And then you have the other extreme, the super expensive methods.
The unified models that try to generate intermediate thought images, they'll decode sometimes hundreds of visual tokens at every single step just to represent a subgoal, like a depth map.
Training that must be prohibitive. An inference would be a nightmare for speed.
It is. And what's really surprising is that even when researchers try to introduce image thoughts more explicitly, forcing the model to switch between text and visual latents, the performance sometimes actually went down on visual puzzles.
So forcing that explicit switch, it adds friction or something.
It seems to.
Yes.
It feels like the model is being penalized for being too prescriptive about its own internal thinking.
So the big realization here is that the model needs a private internal workspace where it doesn't have to declare, okay, I'm thinking in words now, or now I'm thinking in images.
It just needs to think abstractly.
And that's the promise of Mull-Tokens, a simple fixed-length set of latent slots that can represent whatever internal state is needed.
Which brings us to the technical core, the architecture, and importantly, the training paradigm.
So how do they actually work?
Mull-Tokens are represented as a fixed-length sequence of special latent tokens. Let's call them Z1 to K. And critically, they're just appended directly to the input question. And they interact with everything, the image feeders, the text prompt, each other, all through self-attention. They're just empty vessels for any kind of intermediate computation.
But like you said, you can't just toss 40 random tokens in there and expect magic. The model has to learn how to use them.
Right. And the training curriculum is this two-stage process that is absolutely central to making it all work. Let's start with stage one, the warm-up.
Okay, the warm-up.
Stage one is so important because it gives the tokens their initial semantic grounding. They call it supervised anchoring.
And for this, they use those data sets that already have detailed human-generated interleaved text-image reasoning traces, the DCOT.
Exactly. The whole goal is to anchor these latent tokens to real concepts, both verbal and visual.
The textual anchoring makes sense to me. If the ground truth trace's next step is text, you use a standard cross-entropy loss. But if textuality is brittle, and we want these Mull-Tokens to represent visual concepts, how do you force a latent token to look like a depth map without making the model draw it?
That's the really clever part of stage one. If the next step in that ground truth COTI is a visual concept, a sub-goal image, a specific manipulation, they use a trick.
No generation loss.
No generation loss. Instead, they take the hidden state of that specific Mull-Token and they supervise it using a cosine similarity loss against the pre-extracted image feature from a frozen image encoder.
Okay. So they're basically saying, hey, Mull-Token, make your internal abstract representation match the encoded features of this ground truth visual subgoal.
You got it. You're forcing the latent token to internalize the visual data, the object layout, the depth map, without ever paying the cost of explicit visual generation.
So the token learns to represent both verbal logic and complex visual information in the same latent space. It becomes truly modality agnostic.
Exactly. But you raised a good point earlier. If we're anchoring them to these existing and potentially suboptimal human COTI traces, aren't we just baking in those same brittle biases?
Yeah, I mean, human design COTI is often just scaffolding. It's not necessarily the most efficient computational path for an AI.
And that is precisely why Stage 2, relaxed training, is the absolute key to unlocking the system's potential.
This is where it goes beyond just imitation.
Yes. In this stage, all that detailed intermediate supervision is just dropped. The intermediate COTI steps are gone.
So no more cross-entropy loss against the text rationales, no more cosine similarity against visual features.
All gone. The model is trained purely on the final answer likelihood. The Mull-Tokens are now treated as a pure internal compute pipeline, and they're free to optimize their own latent trajectories just to maximize end-task performance.
So this is where the model finds its own most efficient internal reasoning path, totally unbound by how a human might have done it.
That transition is critical. It's the move from supervised mimicking to self-optimized computation.
And there was a final step too, right? A stage 3, using some kind of policy optimization.
Yeah, they use GRPO-guided reinforcement learning with policy optimization just to refine the process. It's mostly about stability. It explicitly rewards latent chains that causally contribute to the correct final answer.
So it makes sure the model doesn't find some weird shortcut that ignores the Mull-Tokens entirely.
Exactly. It guarantees the internal thinking is actually being leveraged.
Okay, so now let's get to the evidence. The empirical results, which really seem to confirm that this whole multi-stage, multimodal strategy is non-negotiable.
It is. They evaluated this approach really rigorously using a Quinn 2.5 VL base model across 4 extremely challenging spatial reasoning benchmarks.
And these aren't simple classification tasks we're talking about.
Not at all. We're talking about BLINK, which is multi-view depth and even IQ tests, SAT Real, which is all about action and motion reasoning, VSI-Bench, which is spatial reasoning inside videos like route planning, and ERQA for robotics action consequences.
A really comprehensive test suite. And the Ablation study in Table 2, that's what proves the multimodal warm-up is the real secret sauce here.
It really does. If they ran the model with Mull-Tokens but gave it no warm-up, just treated them as extra compute tokens, it actually underperformed the baseline.
So just throwing more processing capacity at the problem isn't the answer.
Not at all. The model has to be taught what to do with those tokens.
And the text-only warm-up
Offered only marginal gains. About a 1% improvement over the baseline. So, an incremental improvement, but not enough for these tough visual tasks.
But the warm-up anchoring the tokens to both visual features and text, that achieved the highest lift, over 3% above the direct answer baseline.
Think about that. Just adding a handful of these abstract thoughts, trained to understand both modalities, gives you 3 times the performance lift. It just fundamentally proves the value of that modality-agnostic initialization.
And that initialization is key to another big engineering question. Should these internal thoughts be discrete tokens or, say, continuous embeddings?
Right. And continuous recurrent embeddings, they tend to suffer from error accumulation and instability, especially over longer chains of reasoning.
So if the model has to think through, say, 20 steps, the early steps get corrupted.
Pretty much. And on the efficiency side, continuous embeddings break standard transformer parallelism. They force sequential computation, which slows down both training and inference dramatically.
So what did the paper find?
The paper found that discrete tokens won, hands down. They performed consistently better than the continuous embeddings for all the token counts they tested.
That provides stability, prevents the error accumulation.
And crucially, allows for faster training and inference because they fit perfectly into the parallel architecture of the transformer. That's a huge win for anyone looking at deployment costs.
Okay, but that brings us to the Goldilocks problem. How many tokens, K, do you actually need? Is more always better?
It's a great question. Their analysis on scaling K showed that while the reasoning tasks do benefit from more tokens at first, there's a saturation point.
And then performance starts to degrade.
Significantly, yeah. Specifically when you go above about 40 tokens.
That reminds me of the overthinking concept we've seen in LLMs, where an excessively verbose chain of thought can actually dilute the core insight and lead to worse answers.
It's the exact same idea. For the highest performing reasoning splits, the sweet spot was right around 40 tokens. It's such a powerful computational insight.
You only need a small, abstract compute budget. A few discrete tokens to get these massive performance gains without the overhead.
And this all connects back to the start. The Mull-Tokens approach consistently beat the explicit interleaved image-text approach.
Where the model is forced to declare that it's switching modalities?
Right. It just reiterates that core message. Abstract, modality-agnostic thinking is superior. The less friction you introduce, the better the computation.
Okay, here's a really fascinating application that touches on interpretability. Even though the Mull-Tokens themselves are opaque, the researchers actually explored using them to improve the generation of human-readable text rationales.
That's right. It's a hybrid mechanism. So instead of having the model predict the rationale directly, the model thinks abstractly using the Mull-Tokens first.
And then it generates the text rationale, and then finally it gives the answer.
Exactly. And they found this hybrid approach gets higher answering accuracy than both direct rationale prediction and the interleaved image text thoughts.
Which strongly suggests that the latent Mull-Tokens are providing a superior abstract computational space before the model even has to try and verbalize its process for a human.
And the qualitative insights from the paper are really smart too. For some tasks, like a complex jigsaw puzzle, the model uses the text reasoning alongside the latents to structure its comparison.
But not for everything.
No. For pure spatial tasks, like detecting camera motion or depth changes, it often just intelligently skips the text rationale entirely. It relies solely on the efficient latent thinking to get the right answer.
So the model learns to deploy its verbalization effort only when it's actually computationally useful.
Yes. But we have to acknowledge the elephant in the room that the paper clearly flags.
The lack of direct interpretability.
Exactly. Yeah. Since these tokens are modality agnostic, you can't easily decode them into a single human-readable sketch or a paragraph. The internal reasoning process is, well, it's partially opaque.
It's a black box.
It is. Now, they did observe high semantic consistency. So Mull-Tokens used for jigsaw tasks often mapped consistently closest to concepts like let's compare or final layout. But without a systematic decoding mechanism, the actual trajectory of the reasoning is hidden.
It's a trade-off then. Speed and accuracy in exchange for perfect step-by-step transparency.
That's the trade-off.
Okay, so to summarize the breakthrough here, Mull-Tokens establish a computationally efficient, simple, and high-performance paradigm for multimodal reasoning.
And they deliver those accuracy gains up to 16% on complex spatial tasks, while dramatically cutting the inference overhead you'd get from verbose chain-of-thought methods.
So for those of you working in advanced ML research, this work seems to establish a pretty clear direction.
I think so. The next major leap in reasoning computation seems to be about moving beyond explicit textual or visual steps and into a modality-agnostic latent representation. It simplifies the pipeline and maximizes performance.
It really makes you consider the fundamental goal of AI reasoning, doesn't it? If a handful of latent, fast, and uninterpretable tokens can so significantly outperform verbose, human-readable rationales on accuracy...
Yeah, where are we headed?
Does the future of advanced AI reasoning lie fundamentally in maximizing computational efficiency and abstraction, rather than striving for perfect human interpretability? It feels like we're entering an era where computational effectiveness might just supersede human-friendly traceability.
And if we accept that trade-off, the immediate challenge for researchers is figuring out how to extend this framework to truly novel modalities, things like 3D point clouds or audio, which currently lack those rich, structured, human-annotated key traces you need for that crucial stage 1 warm-up. Data scarcity is still the big constraint on true multimodal generalization.